Okay, we're going to talk today about how to optimize certain quantities under constraints. Remember to maximize a function, for example. Let's say your original function looks like this. If you need to maximize the function, remember that the first thing you do is find the first derivative. Wherever the first derivative is equal to 0, that's where the slope of the tangent line is 0. That's where a possible max could occur. So to optimize something, the first thing you do is take the first derivative, set it equal to 0, see where that happens. The next thing you got to do, though, is you got to ensure it's a max, because the slope of the tangent line could be 0 if it were a min as well. So one way to do that is to look at the second derivative and see if it is always negative, which means that you're concave down. That would prove that something's a max. Now, if you're looking at the function only from an interval from a to b, then you could also check the endpoints along with any places where the derivative is 0, basically any kind of critical values, including places where the function would be undefined or the derivative would be undefined. That could also optimize something. So in this case, let's suppose this is maybe the number 1 and this is, say, 10. If you checked back, and this was your critical value c, if you checked back at the function at values a, c, and b, what you'd find out is that when you plugged in a into the function, you got 1. When you plugged c into the function, you got 10. And when you plugged b into the function, you got 1 again. The largest number, if you check the endpoints along with any critical values, is the place where the max occurs. Another thing to remember is you could also have a situation where you're actually looking for a minimum value. Now, a minimum value is also going to have a horizontal tangent line, which means the slope of the tangent line is 0, which means the derivative is 0. So any critical value would be a point where the first derivative equals 0. One way to prove it's a min is to look at the second derivative. If the second derivative is always positive, that means you're smiley, or in other words, concave up. Which means that the point is indeed a min. If you're not able to find the second derivative and get its sign, then another thing you can do is check all the critical values along with endpoints. The smallest one is the min. All right, so if you're ready, let's go into some examples. All right, so as you've just read in example 1 here, they're asking us to consider a rectangle. So I'll draw the best rectangle here again. Let me try again. Okay, there we go. Now, you know that a rectangle has a length and a width. So if we call one of these side x, for example, you could also call it w for width, but if we call it x, that means that this side must always be x. And if we call the length, say, y, that means the other side is also y, since they have the same length. Now, a perimeter of 10 means that if you added up all these side lengths, you'd get 10, right? So x plus y should be equal to 10 if the criteria there are satisfied. Now they want to know what are the dimensions of the rectangle with the greatest area. Well, notice the word great there. So this is a maximization problem. They want us to find the max. But we're not maxing the perimeter. The perimeter is set in stone at 10. What we're trying to max is the area. So it's the area, or we could call that function A if you like. You could also call it function F if that helps you. Now area of a rectangle is length times width, right? But here, since we've named them x and y, we'll use that. Since this equation has two variables, we don't know how to take the derivative of that without implicit differentiation. So the easiest thing to do would actually be to just get this all in terms of x's. Now if you look at the perimeter equation, that's the same as 2x plus 2y equals 10. Subtract 2x on both sides. y equals 10 minus 2x. So that means that y is equal to, if you divide by 2 on both sides, 5 minus x. So the area is x times 5 minus x. Now remember, to optimize, you've got to take the derivative, right? Well, we have two options here. One is that we could do the product rule as is. Alternatively, we could take the area function, distribute that x, and then just take the derivative of that polynomial. Either way is fine. But you still got this function A for the area. That is right here. Now remember, to optimize, we need to take the first derivative. Now derivative of 5x is 5. Derivative of x squared is 2x. So this is what we got. Now remember, we're looking for places where this is equal to 0. Well, if you just add 2x to the other side of the equation, you end up with x equals 5 halves. But don't forget, you still need to check if this actually is a max. So when you get down to this answer, you wonder, is it a max? Because it could be a min or some other type of place where the derivative is 0. So what you could do is you could consider the parameters on x and y, or you could try and look at the second derivative as well. Now remember that the first derivative is 5 minus 2x, right? That means that the second derivative, which is the derivative of the derivative, is negative 2. Well, since negative 2 is always a negative number, means that you're frowny face or concave down. So because we're always concave down, that means we do have a max. Now we've got the max, we've proven that it's a max. We just gotta go back and make sure that we have answered the question. So they've told us what are the dimensions of the rectangle with the greatest area. So because of that, we do need to give the y dimension as well. Well, remember we had x plus y equals 10, right? And the x value that we found that maximizes is 5 halves, or 2.5. Well, you can use this equation to find y. Remember, we did figure out that y is the same thing as 5 minus x, came from the perimeter formula. So y is 5 minus 5 halves, which is 5 halves again. Same thing as 2.5, right? So basically 2.5 plus 2.5 plus 2.5 plus 2.5 equals 10. So our rectangle is actually more specifically a square. So the dimensions of the rectangle are 2 by 5 and 2 by 5. Or in our original setup, x is 2.5 and we called the length y. So the perfect form in this situation for the rectangle with the greatest area is actually to make it square shaped. So that's an example so far of a real life optimization problem. So when you're done taking notes, remember you can always pause the video if you need to. But if you're ready, we can go on to the next example. Okay, so if you're reading here, notice that we are asked for the smallest, which actually means that we're trying to minimize something here. So we want to make things small. So what are we asked for? 2 positive real numbers whose product is 50 and have the smallest sum. So the constraints of these two numbers, let's call these two numbers x and y. We need to have their product be 50, so let me just give myself some space and write it. We need their product to be 50, and we want to minimize their sum. So just be careful. Remember, there's usually some sort of constraint along with what needs to be optimized, and so don't mix those two up. Their product is 50, so that means x times y must be equal to 50. That's the constraint. We want to minimize their sum, so sum equals x plus y. So notice that this is the function we want to minimize. It's not the x times y. We already know that that's 50. That's the constraint, but we want to minimize the sum. That's what we're asked to do. So s is the function that we're going to be taking the derivative of. Now s equals x plus y. Now just like last time, when we take the derivative with respect to x, we don't want to have y in the way. But notice how you can solve for y easily over here just by dividing both sides of the equation by x. So y is the same thing as 50 over x. Right? And to take the derivative here, you really have two options. You could either do the quotient rule on that second part, or you could rewrite the original function as just 50 times x to the negative 1 and take the derivative as a polynomial. That's what I'll do, but you would get the same answer if you did the quotient rule. So the derivative of x is just 1, right? 50 times negative 1, remember how to take the derivative here. Do it the same way. Pull the power down and then subtract 1 from the power. So this becomes a minus 50 x to the, and when you drop a power by 1, you actually drop it down to negative 2. And of course, that's the same thing as 50 over x squared. Now remember that the derivative needs to be set equal to 0. So if you rearrange this, different ways you could do this, you could add 50 over x squared to the other side. and then multiply by x squared on both sides. But no matter what algebra you choose, you end up with x squared equals 50. So x is the square root of 50. Now, since 50 is 2 times 25, and 25 is 5 times 5, then what happens is square root of 50 has a root there, so square root of 25 is 5. But you still have a square root of 2 under the radical. So this is our potential min, but we don't know at this point for certain if it is actually a min or a max or nothing. So what we can do is we can try to take the second derivative and see if that leads us anywhere. So recall that the first derivative is 1 minus 50 over x squared. So the second derivative, well, derivative of 1 is 0. Here we've got 2 times 50, so that's 100. A negative times negative is a positive. And when you drop the power, you get x to the negative 3. Now remember, that's really the same thing as 100 over x cubed. And since x is positive, because remember they said at the beginning of the problem that don't assume we have any negatives here. Since x is positive, then that second derivative is always greater than 0, which means we're concave. Remember, second derivative, smiley, right? Positive. So we're concave up this time. Which means that even though we don't know exactly what the function looks like, we know it always has concave up. So that means that this is actually a min. And that's pretty much it. They did ask for what two positive real numbers, so technically we only gave them one of the real numbers. So just to give myself a little space here. So x is 5 times the square root of 2, which remember was the square root of 50. Now to get y, remember that their product has to be 50, and so y was 50 over x, right? So 50 over 5 square roots of 2. That's 10 over square root of 2, right? And then rationalize the denominator. You get 10 times square root of 2 over 2, which is just 5 root 2. So what happened was the y ended up being the same value. So it turns out if you take two numbers in this situation, the way to make it that have the smallest total sum is to have the root. And so that's it for this one. Be sure to take notes, and we'll move on to the next example when you're ready. Don't forget you can pause if you need to. But if you're ready, moving on. Okay, I'll use that to draw a better rectangle this time. So the situation here is that we've got a barn like this, and we want to make some corrals on the side of it. Now, the way the corrals go, they're going to share a length with the barn. So you don't have to have fencing for that last bit. Okay, so this is going to be the setup. Straight line right there. So the rancher only has 400 feet and of fencing, and we're going to be trying to maximize the area. So we want the area that the animals are in to be as big as possible. Now, if I call this length X, notice how the rest of those are also length X. So if I call this length X, that's going to be the same, so no need to introduce a new variable there. However, this bottom part right here could potentially be a different length, so I'm going to call it with a new letter. I'm going to call it Y. Maximize means we're looking for a max as opposed to a min, and we're asked to maximize the area. The constraint is that we only have 400 feet. So if you look at the picture here, if we only have 400 feet of fencing, we need to add all the X's and the Y up, and the answer needs to be 400. So X plus X plus X plus X needs to be equal to 400. Oh, I'm sorry, plus Y, of course. Because the Y needs to be, that's part of the fencing as well. This needs to be equal to 400, right? So that means 4x plus y equals 400. Now we're supposed to maximize the area function. Well, area is going to be just going to be x times y. Oops. The reason is, just think about, you don't need to do the 3 rectangles separately because this is just one big rectangle, so its area is x times y. Now, we need to get this in terms of all x's. So if you solved this above for y, you just see that it was 400 minus 4x, right? Then from here, you can either simplify this, distribute the x, or do the product rule. It's your choice. I am going to go ahead and distribute that x. So we've got 400x minus 4x squared. That's our area function. Remember, to try and optimize it, we need to take its derivative. Derivative of 400x is 400, and the derivative of 4x squared, well, that's 8x. Now remember, we want to find where the first derivative is equal to 0. That's the procedure. If you take this equation, add 8x to both sides, and then divide by both sides by 8, that should give you your x value. So what did we find? Well, we found that x equals 400 divided by 8, which is just 50, if you check that on your calculator or do it in your head. So this is great. So we got a nice clean answer, but we always wonder, is it actually a max? Because remember, it could be a min or something else. Well, one way to figure out if it's a max or not is to check the second derivative. Well, remember, our first derivative it's right here, 400 minus 8x. Second derivative is just going to be, what, negative 8, right? That's always negative, which means we're always concave down, which means that on our original function there would be a max there. So yes, it is a max. Now it says find the dimension that maximizes the area. What is the area of that corral? Well, the dimensions that maximize the area, well, the x is 50, right? That's what we just found. So x equals 50 is going to be the ideal. But remember, we also need to know the dimension on the other side. So dimensions of the corral maximize the enclosed area. Y is going to be, remember, it's 400 minus 4 times x. Because if you solve this for y, you get y equals 400 minus 4 times x, this right here. Now, if our x is 50, then that means that y is 200. So the y value is 200. The last thing they want to know, what is the area of this super maximized corral? Well, area equals length times width. So in this case, 50 times 200, and it turns out that the maximum area is 10,000. Since it's area, it's units squared, and our unit was feet. So here's the dimensions, and here's that max area. If you checked a lot of other areas for different dimensions under the criterion, they would all be smaller than 10,000. 10,000 is the biggest area that we can get. Okay, so if you guys are ready, let's try one last example. This one is kind of fun. Okay, so the situation we have here is that we've got a length of wire. Suppose the length is 4 feet. We want to cut it somewhere and use the pieces to cut it into 2 pieces and use them to make both a circle and a square. So for example, I could cut it here at just 1 unit, make a small circle with 1 foot, and make a larger square with 3 feet. But just whatever it is, I want the total area of this and this together to be maximized. So again, just to reiterate, so I've got 4 feet here. And I want to cut it in not necessarily in half, but I want to cut it in 2 parts where I've made a circle and a square, and I want the area total to be maximized. So here's what I'm going to do to start off. I'm going to name a variable. Now, it could be tempting to name the radius of the circle, but I'm going to actually name one of the side lengths of the square. The math works out well that way. So let's suppose that I named one of the side lengths of the square x. Now I know that the perimeter of this thing needs to be the part around the circle and the part around the square. Now, of course, the square is x plus x plus x plus x, right? So the perimeter would be 4x. But the circle, well, what's the formula for the circumference of a circle? Just to remind you here, circumference is 2 pi r, which does require needing to know the radius. Well, we do have the criteria that the perimeter needs to be 4, right? So I can solve for the radius by subtracting 4x on both sides. 4 minus 4x equals 2 pi r. And then just divide both sides by 2 pi. What happens then is I get r equals 4 minus 4x over 2 pi. But I can reduce that to 2 minus 2x over pi. And I can factor out a 2 to make that look nice. So now this is a formula for my radius. So let's get down to the maximization part. So the area, and remember we are wanting to maximize the area, it says that in the problem. Now the area is what you get when you take the area of the square and combine it with the area of the circle. Now the formula for the area of the square is, now remember area of a square is side times side, right? So remember our original square had a side length of x. And remember that the formula for the area of square is side squared, right? So that'll just be x squared because it's x times x. Now remember our circle, if you'll recall this, we did figure out what its radius is, and that's what we got down there below. The radius of the circle is 2 times 1 minus x over pi. That is the work that we found earlier. So remember that the formula for the area of a circle is pi r squared, right? Well, from here, we don't want to do an optimization problem with two variables if we don't have to. So this is x squared plus pi. Remember, pi is just a constant. But the radius is 2 times 1 minus x over pi. This all gets squared because of the formula pi r squared. Now, if we can clean this up a little bit, it'll be easier to take the derivative. Notice how you've got pi and then you've got a pi squared in the denominator. You've also got a 2 squared. So this is really 2 squared, which is 4 pi, and then over pi squared, right? And then you still have that 1 minus x squared part. So this is going to reduce down to x squared plus 4 over pi. 4 over pi is just a constant. Now 1 minus x squared, I'm going to actually leave it like that. You could FOIL it out if you want to and take a derivative of the polynomial, but I think it might be easier just to use the chain rule to get the derivative here. So now that we've got the a formula, well, we can do the a prime, which is the derivative. Derivative of x squared is 2x. 4 pi is just a constant multiplied, so it comes along. Here I'm going to do the chain rule. This is something squared. So its derivative is 2 times that something, lower the power. And then the chain rule tells us we've got to multiply by the derivative of the inside part. Derivative of 1 minus x is just a negative 1. So my derivative really simplifies down to 2x minus, because of the negative here, this is 4 times 2 is 8 over pi times 1 minus x. Now remember, for optimization, you need to take the derivative and set it equal to 0. So if you do that, you just need to solve this for x. So 2x plus 8 over pi x minus 8 over pi. Add 8 over pi to both sides. Factor out numbers attached to x. So x is actually 8 over pi over that, 2 plus 8 over pi, which means that x is approximately, if you round to 2 decimal places, about 0.56. Okay, so at this point we may be wondering, is this a max or a min or something else? Well, the second derivative is not going to be too easy to work with, because if you think about it, this is going to have derivative of 2x is 2, and then you're going to have to figure out the sign of something complicated. Might be better to check the endpoints here. Remember, the second derivative test only works if you can actually prove that the second derivative is always negative or always positive in the interval. So what I'm actually going to do is, instead of checking the second derivative, I'm actually going to check the endpoints this time. Now think about it. Piece of wire 4 feet long, right? And x is the side of our square, right? What are the constraints on x? Well, obviously x must be greater than or equal to 0, right? Because it's a side length. It can't be a negative number. Now, the absolute most that x can be, remember, we only have 4 feet of wire. So if you add 1s all around for x, that's the absolute biggest x could be. That would be if all the wire was used for the square and none for the circle. So you really only need to check the area function at 3 values. At 0, at our critical value of 0.56, and at our endpoint of 1. Well, just a quick reminder, I think it's long since been erased, but remember that our original formula was, once we converted to all x's, was x squared plus 4 over pi times 1 minus x squared. That was before we took its derivative. That's the original area function. Well, if you plug 0 into that thing for x, what happens is this is 0, this is 0, and you just end up with 4 over pi, which is about about 1.27 approximately. If you plug in 0.56 in for x, definitely need to do that in the calculator, so go ahead and check that. That just by coincidence ends up being also approximately 0.56. And if you plug in 1 for x, notice how this whole term right here becomes 0 because you're doing 1 minus 0. So you just get 1 squared, which is just 1. Well, which one of these is the max? Well, the max is the largest value at x equals 0. So we just proved that the max does not occur at 0.56, it actually occurs at x equals 0. Well, what does that really mean? Well, it means that if you have a specific length of wire, you're trying to build both a circle and a square, and you want the area to be maximized, the total area, well, your best bet is to have x be 0, which means that the side length of the square is 0, which means the square actually doesn't exist. So your best bet with a certain length of wire to maximize your area, the perfect use of area is actually a circle. So thanks for your attention.